They slam hard, they're blown to pieces, and the pieces are blown down. That technology, I think, was known back about 82 or 3. It came right off our TSQ 700 series. Okay. Cool. Now, I want to come forward to a concept. Okay. This is the single biggest concept you've got to learn. This is the concept you've got to understand completely. Okay. And this concept applies to the linear and to the FT. And this is what probably drives our users the craziest. Automatic gain control. Okay. Automatic gain control is a solution to the problem. So to understand AGC, you first have to understand what the problem is. The problem comes in this little picture right here. Okay. Now, I have a 7-year-old. Okay. He played t-ball and got his butt kicked. As a PhD scientific geek, I could really not help him much in the whole t-ball. But I had the chance to get back because recently he entered a science competition. Okay. So yes, I know it's highly unethical, but damn it if my kid was not going to come first in the county because his father has access to about $20 million worth of equipment in his lab. So we started off by doing HPLC identification of butterfly species via the chromophores within their wings. Okay. It blew away the kid who was growing some mice with a little bit of dirty water, you know, got first place. I got 30 points higher than the next competitor. Okay. Now, the problem came is I did not want my son to actually understand, so I had to go back and think about for a second and said, what really is HPLC? Why do we, my son wanted to know, why do we see a peak? Why do we see and I actually found an old pen plotter and got the thing hooked up with the UV detector so you could see the pen come up and come back down. So I asked you the simple question, why does the pen go up and come down? I want the 2nd grade response. I don't want no molar absorptivity crap. Why does the pen go up and come back down?
The signal increase.
So the amount of stuff coming at the detector increases and then decreases, right? That's really what chromatography measures. It's the amount of stuff coming off the column. Okay, so imagine if we were to measure the number of ions coming into the trap across those data points of the HPLC peak. Because remember, we don't collect an HPLC peak. What do we collect with a mass spec? Mass spectra. And then we take the mass spectra, we filter information out of them, and we recreate chromatograms. Does that make sense? Okay, so I can imagine that a chromatographic peak is a set of data points where I first had 2 ions in the trap, then 20 ions, then 200, then 2,000, then 20,000, then 200,000. I'm at the apex of the peak. Now as the peak starts to go back, we go back down to 20,000, 200, 2,000, 200, 20, and 2. Does that make sense?
What are you doing?
I'm looking at the spectra across the HPLC peak. Does that make sense to you guys?
So you're doing an experiment where you vary the number of ions in the trap?
Right, because as the HPLC peak elutes, you'll have a number of ions in the trap, correct? Okay, now, look at the spectra of this peptide MRFA, MRFA, methionine, arginine, phenylalanine, alanine. It should weigh 524.3. And we get a nice spectra of 524.3 at 2 ions with the isotopes. At 20 ions in the trap, 200 ions in the trap, 2,000, 20,000. What happens when we go to 200,000 ions in the trap versus 20,000 ions in the trap? We lose resolution. Now, is resolution a setting or is it something we calculate?
Observations.
It's an observation. You don't set resolution, you observe resolution. So the question is, what really causes resolution loss? Okay. Obviously we have poor resolution here because what's really happened is this peak has gotten wider. The distribution of mass measurements has increased. Now, this ion right here should always weigh 524.3 and we should see a nice stick. But obviously the mass spectrometer sometimes measures at 524.1, 524.2, 524.3, 523.4, 523.5. We see a distribution of mass measurements. When we plot those, we end up with a peak. Does that make sense? Now, what happened was, at this point, that distribution of mass measurements became so wide that it mixed this peak and his isotope together and made one fat peak that's unsymmetric. You guys with me? Why? Do we know?
Too many ions in the trap.
Too many ions in the trap. What do we call that effect? That's called space charge. We are seeing space charge effects. Now, the question is, what determines when the ion leaves the trap and goes to the detector? What determines that time?
It's mass.
It's mass to charge. Now take another step forward. It's mass to charge ratio, but what if the mass to charge ratio has to be a constant and it can't change? Why does that particular mass to charge ion not leave the same time as other mass to charge of the same mass? So in other words, if you got one peptide fill in the trap, they all have the same mass to charge. How come some of the ions leave the trap early and some leave the trap later?
Are they interacting with each other?
They're interacting with each other. And what causes them to leave? What electricity, what voltage causes them to leave?
The RF oscillation, the amplitude.
Which RF?
The quad.
Okay, so the dipolar causes them to leave.
Causes them to eject,
Right. Now, the quad causes them to reach the dipolar. So the dipolar doesn't change. That causes them to leave at the right time. So obviously what's happening here is some of the ions are reaching the dipolar at a different time period because they're at a different frequency. So what space charge is some ions moving at a slightly different frequency than their counterparts at the same mass. That's interesting. What causes them to move at that particular frequency? Take the step back. You just said it a minute ago, now say it again. What caused them to move at a particular frequency? What voltage?
The
quadrupolar. So obviously some ions are moving at the quadrupolar applied voltage, and some ions are moving at a frequency caused by a quadrupolar applied voltage and some other RF. And where's that other RF coming from? Other ions. Think about an ion. What is it? It's a charge moving in a shape. What is RF? RF is a charge moving from one plate to another. So what happens is the ions around me create a separate RF field. And the more ions, the more RF field is measured by me. So my voltage that I experience is not the applied RF. It's the applied RF plus the RF of the ions that are actively around me. And because the applied RF is different than the RF I feel, if I'm in a very dense cloud, if I'm at 200,000 ions sitting around me, that additional effect is much larger and will actually cause me to leave the trap at the wrong time because my frequency is incorrect and I come into resonance at the wrong time, and hence I leave a little bit later than my buddies did. Does that make sense? So, which spectra is acceptable? Anything up to 20,000. We actually go as high as 30,000. Above 30,000 ions, we see noticeable shifts in mass, hence loss of resolution. Okay. Is it acceptable for you guys to be off 0.4 m over z?
linear ion trap?
No, because if it's a triply charged ion, you're off almost a Dalton and a half. Okay, and you guys would be calling me on the phone. So the problem I have to solve is how do I maintain less than 20,000 ions in the trap? Okay, how do I stay right here? The problem is if I upper limit you, then you guys get upset because you have poor dynamic range, which really is the heart of the proteomics issue we have to solve, right? The whole problem in proteomics is everyone can identify always the same 6 proteins in a sample. I'm not impressed that you can identify albumin, myostatin, okay, and transferrin. Everyone does that. The key is to get to those proteins that are 3 orders, 4 orders, 5 orders, 6 orders of magnitude lower than the main proteins. You need dynamic range. You need to be able to operate up here on some scans, and other scans operate down here with equal data quality. The way we do that is AGC. We cheat. Before every real scan, which we call an analytical scan, we do a pre-scan. We fill the trap for 1 millisecond.